Next is an optional section for this lecture. I will talk about parameterization. Actually, in the planetary boundary layer, the math here is actually one type of parameterization. So in the world of atmospheric science, we often use model to do simulations, right? So if we have grids like this and we have some representations of different variables at these grid points, then the things happening inside, the smaller scale things happening inside, we will need some sort of, you can say that it's a projection, or you can say that it's a relationship. We're relating things here with the grid points resolution. So we will use some other types of variables. For example, if you have the resolution of 50 kilometers, and then if you have clouds like these, they're with smaller size, because you don't have the representation for all the things inside. It's a subgrid scale. We need to relate the things on the grid points with the smaller scale stuff. We need to have an equation, and that's what we call parameterization. So we reduce all the information and smaller scale processes to the variables at the grid points. And why do we do this? Because at the grid points, the model could deal with them. The model cannot deal with things inside the grids. Okay, and it aims at produce like a collective result representing all the things happening with just fewer variables here. Okay, so because we don't have the complete description of everything, okay, but in this course we talk about turbulent flow, so we don't have the complete description, so we always have more unknowns than the number of equations, and a lot of the equations are not closed, so we need parameterization to close the equations. So in this course we always talk about this. We have the things that we don't have equations for, and then we have the things that we have the equations for, and then we relate them so that we can close the equations. Okay, and if you're interested, you can take a look at this book. It's the parameterization schemes for atmospheric models, and we have different parameterizations as you can see. So because, for example, the land surface atmosphere interaction is very complicated. That's why we need to do parameterization for this. And also in this course, we talk about planetary boundary layer and turbulence parameterizations because it's just too complicated. We cannot represent everything in a model, so we need parameterizations. And if you have the math, then you can put that in a model, right? So another type of parameterization is convective parameterization, because you don't have the representation for all the water vapor, every dot of them. You cannot have, you simply cannot have the representation of all the things. So we need to have to guess if it's gonna rain or not, okay, according to some of the measurements, or according to some of the variables that we have, for example, moisture and temperature, things like that. Okay, and also radiative transfer is very complicated. I don't know if you know about this, but the math is very complicated, and the model will need a lot of computational power if we want to resolve everything. But most of the times it's just parameterizations in the model. Okay, if you're interested, please take a look at the book. So in this course, we talk about these. So the basic idea of parameterization is actually an approximation to nature. So we use the profile of the mean wind to guess the situation of the turbulence. And it actually replaced the true equation because we do have the mathematical representation for the change of this term over time, right? But we're not using that. We are approximating this with some other things. Okay, we don't want to do the we don't want to use the true equation for this term because we have a lot of limitations, because we could have the situation where we don't know about the processes, and we also have limited computer resources. So this is why we do this. And we hope that this kind of assumption would be adequate, given that we have a lot of measurements, right? So that's why for the planetary boundary layer people, they need to do a lot of measurements. So in this course, we have only talked about the first order closure, and actually we have higher order of closure. We have local closure system schemes, we have non-local closure system schemes. So if you are interested, you can take a look at the textbook. And in this course, we have talked about the constant eddy viscosity approach. We have also talked about the mixing length theory approach. We have the mathematical representation for K. We also have the K in terms of the friction velocity. Okay, and then there are also other schemes that we can use for the value of K, but we didn't go through all of these, so this part is optional. Okay, remember that these three are applicable when you have a neutral situation in the atmosphere. Okay, you are gonna have to prove this. I didn't do this for you, so I think this one is pretty easy. So this is only applicable in the surface layer. Okay,